Okay, so today, let's look over here at our learning goal, first of all. We were working with substitution yesterday. We're going to work with it again today. I can use substitution, so in other words, putting a number value in for a variable to determine a limited range of values for two variables. So today we're going to work with two variables all the time in what we're going to practice here. And we're going to be subbing in some numbers, but we're going to have to find those numbers. We're going to determine what they are, okay? So it says circle, here's our directions first of all. Circle the number of possible values that can be substituted for the variable or variables in each equation so that the equation is true. So let's circle number one here. There's number one. We have three choices of an answer, A, B, or C. We have to determine if x and y can be only whole number, can be any whole number, excuse me, in the equation x plus y equals 3, then there is. Well, then we're trying to determine, is there only one value that will make that true? Is there an infinite number of values? In other words, we couldn't even begin to name them all. Or is there a limited set of values for the variable? But here's what's really important first of all. We need to underline this, any whole number. That's a really important piece right there. That phrase we cannot ignore. They want any whole number. So x and y, whatever we pick, they have to come from the whole number set. Well, we better talk about the whole number set then. What's the whole number set? You got to know that. What is the whole number set? Anybody know where the whole numbers start? Can you tell me that much? Zero? Zero. They start at 0. Can you tell me how much distance there is between them? If we start at 0, what do we do from there? What would be the next whole number? What? 1. Okay, so it goes up by, from 0 to 1, there's a distance of 1 unit. So from 0 to 1, what would be the next one? 2, and the next one? 3, and you just keep going up by 1s, right? Okay, so let's put that up here first of all. Let's write, so we have this information. Whole numbers. This is really important that we know what the whole number set is. Put that fancy little bracket there. We're going to show, this is called set notation. What it really is it's kind of like a U laying on its side with a V on its side with another U below it. So you just got to try and make this little curly Q bracket. It starts at 0, as Kira said. And as the rest of us said, it keeps going up by 1. So 1, 2, 3. Can we begin to name the whole number set, do you think? Really? In other words, we can count forever and never and live long enough to get, and you even know what some of those numbers are way out there. It goes on forever, so we're going to go dot, dot, dot. And then we're going to close our set. That's the whole number set, and that's important that we know that, because if we can only pick whole numbers, then we got to make sure that the numbers we choose come from that set. And then our equation is this, so we need any whole number that will work in that equation, x plus y equals 3. So let's go up here and let's write our equation down. X plus y equals 3. You're not going to be able to write really large, but you want to write big enough to be able to see, because we're going to do our work here in this margin over here, okay? Well, we need to pick some numbers for x that when we add it to our y value, we're going to get 3 from the whole number set. So let's just start with 0 and see. There's something that if we made x 0, what would y be then? 3, because 0 plus 3 is 3. Okay, so those two numbers work, don't they? Okay, give me another set of whole numbers that might work. Wait. 1 and 2, because 1, when x is 1, then y would have to be 2, because 1 plus 2 is 3. Okay, give me another set of whole numbers that works. Any more? Is that it? Is there any others? I think there are. Could x be 2? Because then if x was 2, what would y be? 1. Okay, well, why did you stop on me then? Oh, could x be 3? Yeah. And because if x is 3, then y is 0. Okay. Well, now, can we go any further? Can we have 4? What do you think? Can we use 4 for x? Why not?
Because this is in subtraction.
Oh, because then we'd have to subtract instead of add, wouldn't we? Yeah, we'd have to subtract rather than add. We'd have to take 1 away, which is really, what is taking 1 away the same as? Subtracting 1 is the same as subtracting 1 is the same as adding, say it, what is it? Negative 1. Remember, add the opposite. So subtracting 1 is the same as adding the opposite of 1. The opposite of 1 is negative 1. So is negative 1 in the whole number set? No, negative 1 is not a member of the whole number set, so this one stops. So we have what we call a limited value set of values. So we're going to put a box around this, and we're going to show, this is our work that goes with it. We're going to say there's a limited set of values for the variables that make the equation true. We just found them. There's 4 pairs of them. It's limited. It can't go on forever. Okay, questions? Because you're going to have to be able to do this, so I want to know if you can. Okay, let's just move on, then let's try the next one. Okay. It says, if a can be any integer in the equation -4 plus a equals 1, then there is same choices, exactly 1, an infinite number of choices, or a limited set of choices. Well, now we got, so any integer, we're going to underline that. That's important, integer. And then we have this equation. Oh, integers. What are those? Anybody know what the integer set is? Harley?
It's negative and positive.
Oh, so it's, like, give me an example.
Like -1 and
Yeah, so let's go up here and let's also show the integers. The integers. It's really important that we understand these words, because otherwise how can we follow what the directions say, right? So the integers, we're going to make our fancy bracket again. And this time, Harley's right, the integer set is a whole numbers and their opposites. So here's what we're going to do. We're going to start with 3 dots to show we can't begin to give all of them in the direction going left. And we're going to start with -3, then we're going to go to -2, and then we're going to go to -1, and then we're going to go to 0, and then we're going to go to 1, and then we're going to go to 2, and then we're going to go to 3, and then we're going to ... So we have a good picture of what does the integer number set look like. So it goes on forever in the negative direction. It doesn't have a starting point. Goes on forever in the positive direction. It doesn't have an ending point. But what is the distance between every number in the set? How much distance is there between the numbers? Danny? 1. It's changing by 1s again. It's going up by 1 every time when you're heading to the right. It's going down by 1s when you're heading to the left. Okay, so there's our integers. Well, now we know we can pick numbers from the integer set for our equation. So let's put -4 plus a equals 1. How many variables do we have to deal with this time? 2? We just have 1, don't we? We just have the a, don't we? So we're looking for how many values can we substitute in for a that will make this equation true. Wait.
I was going to say the answer.
You're going to tell me what you think a could be? Okay, what do you think a could be?
Positive 5.
Positive 5. Okay, so he says if you take negative 4 and you add 5 to it, you get 1. Do you agree? You don't, huh? Wait, could you convince them that negative 4 plus 5 is 1?
Let me teach you. So you start at -4, and then you go 5 spots up. 5 positive.
Okay, the positive direction, okay? So 1, 2, 3, 4, 5. Oh, look at where we land. Is Wade right?
Yeah.
Uh-huh, he is. Okay. Can you think of any other numbers? That if you added it to negative 4, you'd get positive 1. Is there any other number from the integer number set that when you start here at negative 4, you're going to end up at positive 1? Can you think of any other number? I don't think there is one, is there? No, so A equals what? Only 5. A can only equal 5, which means which multiple choice answer should we select? Exactly one value for the variable makes the equation true?
Yes.
Yeah, exactly 1. We only found one value that made the equation true. Here it is. We only found the 1. Okay, questions on that one at all? Okay, so what we're trying to make sure we're understanding is variables stand in for number values. Sometimes the variable can stand in for more than one number value. Other times it can only stand in for the 1. And then sometimes maybe there's an infinite number of them. Okay, let's look at number 3. If x and y can be any whole number, what do you suppose I'm going to say we should underline? Any whole number. In the equation x plus y equals 5, then we're going to check it out. How many choices do we have for the variables this time? So we got 2 variables again. Let's write our equation down. Let's make a little xy table to help us. Whole numbers, they start where? Where do the whole numbers start again?
1, 0.
0. So let's start with 0. 0 plus what is 5? 5. So y would be 5.
1 and 4.
Next whole number is 1. 1 and 4. 1 plus 4 is 5. 2 and 3.
3 and 2.
3 and 2. Oh, maybe this is one of those where we could go on forever. Huh? 4 and 1. Okay. And 5 and 0. How about 6? No, because now we can't add something to 6 that is a whole number, can we? We'd have to subtract the whole number, and then subtracting a whole number is the same as adding the opposite of it, which doesn't make it a whole number anymore and all. So I guess there's what? A limited set of values. We just found them. It's a little bit longer than our last one was, but it's a limited set of values. In number 1, we had a shorter list, but this one stopped also, didn't it? Just got just a little bit more. Okay. Let's look at number 4. If A and B can be what? Any whole number. In the equation A plus B equals B plus A, then there is A plus B equals B plus A. Any whole number. Well, you gotta pick different numbers for A and B though, right? So, let's just start with, let's just try one. If A is what? What do you want A to be? 0? How about B? What do you want that to be? 0? 2, okay. 0 plus 2 equals, well, B is 2, A is 0. 0 plus 2 is 2, and 2 plus 0 is? Okay. We don't have a whole lot of space over here, do we? So do you think we can right now stop and say, hey, wait a minute. What is this statement showing us? Remember that property we talked about? We already discovered this pattern. Would it matter what we picked for A and B? Why not? Because what property is being shown right here? A plus B equals B plus A. What property is that called again? Commutative property. We have commutative property. So we're going to put commutative, let's write it. And commutative means add in any order. It does not matter. Commutative, add in any order. So how many different sets of numbers do you think we could choose for A and B? 1, limited, unlimited, infinite, right? So we would say there's an infinite number of values for the variables that make this one true because we know this is commutative property. This general pattern says just keep picking numbers till you can't stand it anymore. They're all going to work. Questions? Okay, let's do one more then. If m and n can be any whole number, well, that's kind of important. In the equation, m plus n equals 12, that's important also. Then there is, well, looking again, do we have just one? Do we have an infinite number? Or do we have a limited set? So m plus n equals 12. Whole numbers. So where do we start? What whole number do we start with? 0. That makes, if m is 0, n is 12. Okay, well, go ahead and make this table. It's a long one. Go. Make it work. I might want to write it too big, or you might have to have your table split over and, you know, whatever. But maybe it's going to go on forever. I don't know. Hey guys, here's how you can check to see if we're right. As the m's go up by 1, what do the n's do? They go down by 1, don't they? So there's a pattern going on there too. Now, I want to point something out because I don't want you to think that two variables can't ever equal each other. I told you not to pick same values for your variables because they don't always, that doesn't necessarily always tell us if we have a pattern going on or not. Notice right there in our table, when m is 6, n can also be 6. That's okay. I just don't want us, when we are picking values, sometimes just to test a pattern, I don't want you picking same values because then it doesn't necessarily test the pattern well, okay? So this is okay that both m and n equal 6. In this case, it's okay. So can this table keep going? Okay, if m is 13, What would n be? That'd be -1, wouldn't it? Take away 1, would that be plus a -1? Is -1 a whole number? No, so we're done with this table, aren't we? Even though it's kind of long, we're still done with it. We have a limited set of values for the equation that make it true. Okay. Are we ready to try the backside now? It's even more challenged. Okay. Anybody have any questions though before we do move on? I don't want to leave you not understanding. And I'm gonna move on. Okay. Now our directions say, in the chart provided, write examples of pairs of whole numbers. Hey, that's a big deal. They're telling us right there, you can only use pairs of whole numbers that can be substituted for the variables x and y to make a true statement. So we have here this equation, x divided by y equals 4. We're supposed to use the chart to solve this problem. Show 4 examples of pairs of whole numbers that can be substituted for x and y in the equation. Well, we know what the whole number set looks like now, right? So we need a number for x that when you divide it by the number you choose for y, that you get the quotient 4. Can anybody give me a pair of whole numbers that when you divide them, you're going to get 4? Celia? 8 and 2, okay, so when x is 8, y is 2, in other words, 8 divided by 2 equals 4. Is that true, class? Okay, put that off to the side just for us to prove that we got a good pair. Okay, Kaden? Pardon?
4
Okay, when x is 4 and y is 1, 4 divided by 1, sure enough, that equals 4 also, doesn't it? And they're a pair of whole numbers. Another pair of whole numbers that would work. Are there any more? They want 4 of them. Come on, we gotta come up with a couple more, don't we? Joanne? 12 divided by 3. Okay. Try that one. When x is 12 and y is 3, is 12 divided by 3 4? Yes, it is. Tyler? 20 divided by 5. So when x is 20 and y is 5, is 20 divided by 5 4? And it is, isn't it? What do you think? You think we could keep going if they wanted us to do 4 more? Could we do it? Could we find 4 more? Do some of you have some that we didn't use yet? Yeah? What could we find? And after we found those 4, do you think we can find 4 more? Even 4 more? Over 4 more? Well, how many do you think there are then? Do you think this is a limited number or do you think this is an infinite? This is an infinite. We can keep going forever with this. So let's just put it just off to the sideline here, that there would be an infinite number of pairs. There would be an infinite number of pairs in this one. And I keep on the same thought we were having on the front side. But they only asked us to show 4. Okay, let's move on to number 2, where it says use the chart to solve the problem, show 8 examples this time. Here's our equation. So we need the value for x that when you take away y, you're going to get the difference of 4. So Kira, what's the first one going to be?
12 minus 8.
12 and 8. Okay, so 12, take away 8. I'm going to have to write a little bit smaller this time because I got to get 8 of them in here. Is 4. Okay, that one works. Harley. 3 and 1. Okay, 3 and 1. 3 take away 1 is 4.
Never mind.
What can we change that x to make this work? 5, yeah, let's change that x to 5. And then it'll work, won't it? 5 and 1, how about that? Does that work? Yeah, okay. Wait,
8 minus 4.
8 and 4. 8, take away 4, is that 4?
Yes.
Okay. If I haven't heard from you, you gotta come up with one, get your hand up for me. I've heard from you before. Mikey, I haven't heard from you for a while. 14 and 10, she says. 14 take away 10 is 4. I agree. Okay, that pair works. Got one for me, Hannah? Think on it. Dan, you got one for me? 9 and 5. 9 take away 5 is 4. How many do we have so far here? I think we got 5 of them. We need 3 more. You got one for me now, Hannah? Okay, what is it? 24 minus what? Did you say it and I didn't hear it? Nope, remember we gotta use this equation, minus. 24 minus what gives you 4? Come on, you got it. No, help roll class.
16.
No, 24 minus what gives us 4? 20. There, okay, I think maybe this will help you out. Let's just stop for a second and look at the pattern that's happening in this table. Every time you look at a pair of numbers, every time we look at a pair of numbers, 12 and 8, 5 and 1, 8 and 4, 14, 10, 9, 5, 24, 20, they are all how many units away from each other? How many units apart are they on the number line? 4 units. So you know what, maybe what you should do is think about a number that you can put here and add 4 to it so we can come back over here, be 4 units away. Give me a number here that we don't have in the Y column. Sylvia? 12. Okay, well if we're going to use 12, then we add 4 to it and we get 16. Let's see if 16 take away 12. Oh, sure enough, that equals 4, doesn't it? Okay, how many do we have now?
7.
7. We got 1 to go. Sierra, you got one for me?
10 subtract 6.
10 subtract 6. And that does equal 4. We got 8. Is that all there are? Is that all there are? Do you think we could do this for a long time?
Yeah.
We could keep finding whole numbers on the number line that are 4 units apart, couldn't we? Forever. So how many pairs could we come up with? Infinite number of pairs. They said 8, but we're saying, you know what? Good thing you asked us to stop at 8 because there are an infinite number of them and we want to do something other than this with the rest of our life. Infinite number of pairs. Even though we only had to find 8, we know we could find about 8 million more. Plus. Okay, and our last one, number 3. Okay, number 3, it says, use 8 examples again. We can do this, we got this. Of whole numbers, of course, and there's our equation. X times a half equals Y. Or in other words, half of X gives you Y. Now what kind of numbers would be nice X values to choose, because it's easy to divide them by 2, or in other words, find half of them. What kind of numbers should we look for? Wait,
10.
like 10, but what kind of number is 10?
Whole number.
It's a whole number, I will give you that. Cheyenne? Even numbers, because even numbers all are divisible by 2. Isn't it easy to find half of even numbers? Is half of odd numbers so fun? Like half of 5? Half of 5? No, not that we can't find it, but is half of 5 going to be a whole number Y value? No. What is half of 5?
2.5.
2.5. Is 2.5 a whole number? No. So we pretty much are stuck choosing what kind of numbers? Evens, aren't we? Okay, so let's go. We need 8 even numbers for x. It's that easy. Danny? Oh, wait a minute. Don't say never mind. How about 0 for y then? 1, 0 times a half. Half of 0. Well, 0 times anything, class, is what? 0. Oh, look at there. Y can be 0. It's okay. 0. They can, remember I said sometimes they can have the same values? Okay, wait.
8 and 4.
8 and 4. Okay, so 8 and 4. 8 times a half equals 4. Remember, the only thing that's staying the same this time is the times 1/2. We're taking the half times our x value, and it produces our y value. So the only thing that should look the same is our times 1/2. Okay, Harley?
10 and 5.
10 and 5. In other words, if you take 10 times a half, or take half of 10, you get 5. Give me another pair. Kaylee, I haven't heard from you yet. Can you help me out? Kaylee, not Keely, not yet. Got one for me, Kaylee? Nope, you want to think about it for a little bit, Sam? Can you give me one?
8 and 16.
8 and 16. Okay, so should the x be 8? Or should the y, or should the y should be 8? Oh yeah, because we're going to take half of the x, and half of 16 is 8, isn't it? 16 times a half is 8. Okay? So it matters which one is which, right? Okay, Caden, you give me one next.
6 and 3.
6 and 3. So 6 times a half is 3. So again, looking in our table, can you see what's happening here? If we thought of it as division, what happens? When you go from x to y, you're doing what? You're dividing by 2. Okay, pick an x value, divide it by 2, and you'll have your y value, right? Isn't that what you got to do? Danny, what's yours? The same, which one? The same one that just got put there? Okay, same one. Kira?
4 times 2.
4, not times 2, but 4 times a half would be 2, right? Wait,
24 and 12.
24 and 12, because 24 times a half is 12. Or in other words, remember what I said? 24 divided by 2. How many do we have? We need one more. Okay. Got one for me yet, Kaylee? No? No? Okay. Ikea? 12 and 6. Or in other words, 12 times a half is 6. Or 12 divided by 2. Multiplying by a half is the same as dividing by 2. Could we keep going? Have we exhausted all the even numbers for x yet? No, there's a ton more, aren't there? So what are we going to say? Infinite number of pairs. So in other words, again, we have to understand sometimes there's only one value for the variable. Sometimes there's a limited set of values for the variable. And sometimes there's an infinite number of values for the variable. Okay, no questions?